My name is Nowinski, and this is Lab 1 focused on a real-world experiment highlighting constant velocity and Newton's second law. In this lab, I performed a real-life constant velocity observation, created a computer model using GlowScript, compared the expected and observed data, and discussed relevant physics principles. The purpose of the lab was to dive deeper into Newton's second law, specifically the relationship between zero net force and constant velocity. Another goal consisted of using the position update formula and velocity update formula in order to predict the motion of an object with constant velocity. In order to accurately complete these goals, I had to utilize both Tracker and GlowScript. The fundamental focus of this lab is on Newton's second law, which states that if the net force acting on an object is zero, the object will experience no change in its motion. Therefore, if an object already in motion does not experience any change in the forces acting upon it, the object will have constant velocity and change in momentum. For my experiment, I rolled a medicine tube with a mass of 0.06 grams and a diameter of 0.00381 meters across a flat desk. The system is the tube, and the surroundings are everything else, including my hand, which provided the initial force for the tube. Here is the original video of the motion. Through this image, which is a screenshot taken from Tracker, it can be seen that I marked the center of the tube as it rolled across the surface in the x direction. The graph in the top right shows the positive linear relationship of position versus time. The axes are currently oriented in the positive x direction. However, if the axes were reversed, there would be some changes to some key figures. Magnitude would stay the same, as the formula involves taking the square root. However, direction and the sign of velocity would be flipped. I was able to take the initial position from the table given in the bottom right and calculated the initial velocity by subtracting the first x position by subtracting x1 minus x0 over t1 minus t0, yielding 0.0506 meters per second. For my computational model in GlowScript, I updated the mass to match that of the tube, updated the initial conditions of position and velocity based on the tracker information, updated the delta t in time for my specific time steps and ranges, and updated the net force to 0 to match our assumption that net force is in fact 0. Here is my computational model showing the object moving in a positive x direction and the position versus time graph having a positive linear relationship. On the left, you can see the position of the observed versus expected models with the time steps, and when graphed together, we can note that the expected model is perfectly linear due to the assumption that velocity is perfectly constant as there is no net force, while the expected model is less linear due to discrepancies that I will discuss next. While not exactly the same, both models follow the same positive linear trend. Some possible reasons for discrepancies between the predicted and expected models include an external force in the experiment, such as friction, drag, or air resistance that are not accounted for. Further, there is the possibility of the surface not being level, the camera not being perfectly still, or human error on my end while adding my center of mass marks or the calibration line. What does this mean for net force being equal to 0? Net force of 0 is the sum of forces acting on an object, including gravity and friction, that yields constant velocity. However, we ignore many of these forces for the assumptions in the experiment, and it is not possible to know all the pushes and pulls acting on the object in the real world. To conclude, the lab focused on the real-world application of constant velocity comparing a predicted versus expected model of a rolling medicine tube. The experiment was not perfect due to the aforementioned discrepancies, and could be improved through accounting for other forces, using a fully leveled surface or a more stable camera. Thank you.